Welcome to the session Application of Laplace Transforms and Laplace Transforms of Some Useful Functions. Application to differential equations. Laplace transforms can be used to solve ordinary as well as partial differential equations. We shall apply this method to solve only ordinary linear differential equations with constant coefficients. The advantage of this method is that it yields the particular solution directly without the necessity of first finding the general solution and then evaluating the arbitrary constants. Consider the following linear differential equations with constant coefficients: d raised to n y by dt raised to n plus k1 into d raised to n minus 1 y by dt raised to n minus 1 plus k2 into d raised to n minus 2 y by dt raised to n minus 2 plus etc. plus kn into y is equal to f of t, where k1, k2, etc. kn are constants with the n initial conditions: y of a is equal to b1, y dash of a is equal to b2, etc. y raised to n minus 1 of a is equal to bn. This equation is known as initial value problem. Steps to solve the differential equation. First one, take Laplace transforms on both sides using the notations L of y is equal to y bar and L of f of t is equal to phi of s. Second one, use the given initial conditions. Third one, simplify the algebraic equation in the form y bar is equal to f of s. Fourth one, take inverse Laplace transforms on both sides to obtain the desired solution. Example 1. Solve the equation d cube y by dt cube plus 2 into d square y by dt square minus dy by dt minus 2y is equal to 0, where y is equal to 1, dy by dt is equal to 2, d square y by dt square is equal to 2 at t equal to 0. Solution. The given equation is y triple dash plus 2 into y double dash minus y dash minus 2 into y is equal to 0. Taking the Laplace transform on both sides, we obtain s cube into y bar minus s square into y of 0 minus s into y dash of 0 minus y double dash of 0 plus 2 into s square y bar minus s y of 0 minus y dash of 0 minus of s y bar minus y of 0 minus 2y bar is equal to 0. Using the given conditions y of 0 equal to 1, y dash of 0 equal to 2, y double dash of 0 is equal to 2, the equation reduces to s cube plus 2s square minus s minus 2 into y bar minus s square minus 2s minus 2 minus 2s minus 4 plus 1 is equal to 0, or s cube plus 2s square minus s minus 2 into y bar is equal to s square plus 4s plus 5. Therefore, y bar is equal to s square plus 4s plus 5 all divided by s cube plus 2s square minus s minus 2, which is equal to s square plus 4s plus 5 all divided by s minus 1 into s plus 1 into s plus 2. That is equal to 5 divided by 3 into s minus 1 minus 1 divided by s plus 1 plus 1 by 3 into s plus 2 by resolving into partial fractions. Taking the inverse Laplace transforms on both sides, we get L inverse of y bar is equal to 5 by 3 into L inverse of 1 by s minus 1 minus L inverse of 1 by s plus 1 plus 1 by 3 into L inverse of 1 by s plus 2. That is, y is equal to 5 by 3 into e raised to t minus e raised to minus t plus 1 by 3 into e raised to minus 2t. That is, y is equal to 1 by 3 into 5 e raised to t plus e raised to minus 2t minus e raised to minus t, which is the desired solution. Note: boundary value problem can also be solved by Laplace transform method. The following example illustrates the method. Example 2. Solve the boundary value problem d square y by dt square plus 9y is equal to cos 2t with y of 0 is equal to 1, y of pi by 2 is equal to minus 1. Solution. Let y dash of 0 is equal to c, a constant. Then taking Laplace transforms on both sides, we get s square into y bar minus s into y of 0 minus y dash of 0 plus 9y bar is equal to s divided by s square plus 4, which implies s square plus 9 into y bar minus s minus c is equal to s divided by s square plus 4, which implies y bar is equal to s divided by s square plus 4 into s square plus 9 plus s divided by s square plus 9 plus c divided by s square plus 9, which is equal to 1 by 5 into s by s square plus 4 minus s by s square plus 9 plus s by s square plus 9 plus c by s square plus 9. That is equal to 1 by 5 into s by s square plus 4 plus 4 by 5 into s by s square plus 9 plus c by s square plus 9. Taking inverse Laplace transform on both sides, we get L inverse of phi of s is equal to 1 by 5 into L inverse of s by s square plus 4 plus 4 by 5 into L inverse of s by s square plus 9 plus L inverse of c by s square plus 9. That is y of t is equal to 1 by 5 into cos 2t plus 4 by 5 into cos 3t plus c by 3 into sin 3t. Now from the given condition y of pi by 2 is equal to minus 1, we have minus 1 is equal to 1 by 5 into cos 2 pi by 2 plus 4 by 5 into cos 3 pi by 2 plus c by 3 into sin 3 pi by 2. That is minus 1 is equal to minus 1 by 5 minus c by 3, which implies c is equal to 12 divided by 5. Hence the particular solution is y of t is equal to 1 by 5 into cos 2t plus 4 cos 3t plus 4 sin 3t. Solution of simultaneous linear equations with constant coefficients. Consider the first order simultaneous linear equations with constant coefficients as follows: a1 into dy by dt plus a2 into dx by dt plus a3x plus a for y is equal to f of t, b1 into dy by dt plus b2 into dx by dt plus b3x plus b for y is equal to g of t, where x and y are two dependent variables on the independent variable t and all ai's and bi's are constant terms. To solve this, the following steps may be used. First one, take Laplace transforms of both the equations using the notations L of y is equal to y bar, L of x is equal to x bar, L of f of t equal to phi 1 of s, L of g of t is equal to phi 2 of s. Second step, use the given initial conditions and obtain two equations in x bar and y bar. Third step, solve for x bar and y bar so as to obtain x bar is equal to f1 of s and y bar is equal to f2 of s. Fourth one, take inverse Laplace transforms and obtain the solution x of t and y of t. Example 3. Solve dx by dt minus y is equal to e raised to t, comma dy by dt plus x is equal to sin t, given that x of 0 is equal to 1 and y of 0 is equal to 0. Solution. Taking Laplace transforms of both equations, we get s into x bar minus x of 0 minus y bar is equal to 1 by s minus 1, which implies s into x bar minus 1 minus y bar is equal to 1 by s minus 1, which implies s into x bar minus y bar is equal to 1 plus 1 by s minus 1, which implies s into x bar minus y bar is equal to s divided by s minus 1, and s into y bar minus y of 0 plus x bar is equal to 1 by 1 plus s square, which implies s into y bar plus x bar is equal to 1 by 1 plus s square. Solving for x bar, we get x bar is equal to s square divided by s minus 1 into s square plus 1 plus 1 divided by s square plus 1 the whole square. Taking inverse Laplace transform, we get x of t is equal to L inverse of s square divided by s minus 1 into s square plus 1 plus L inverse of 1 divided by s square plus 1 whole square. That is equal to 1 by 2 into e raised to t plus cos t plus 2 sin t minus t cos t. Now from the given second equation, we have dy by dt is equal to sin t minus x, that is equal to sin t minus 1 by 2 into e raised to t plus cos t plus 2 sin t minus t cos t, which is equal to minus 1 by 2 into e raised to t plus cos t minus t cos t. Integrating both sides, we obtain y of t is equal to minus 1 by 2 into e raised to t plus sin t minus cos t minus t sin t plus c, where c is the constant of integration. From the given condition y of 0 is equal to 0, we obtain 0 is equal to minus 1 by 2 into 1 plus 0 minus 1 minus 0 plus c, which implies c is equal to 0. Thus, y of t is equal to 1 by 2 into cos t plus t sin t minus e raised to t minus sin t. Hence, the required solution of the given simultaneous equations is x of t is equal to 1 by 2 into e raised to t plus cos t plus 2 sin t minus t cos t, comma y of t is equal to 1 by 2 into cos t plus t sin t minus e raised to t minus sin t. Unit step function. Definition. The unit step function u of t minus a is defined as follows. U of t minus a is equal to 0 for 0 less than or equal to t less than a, and equal to 1 for a less than or equal to t less than or equal to infinity, where a greater than or equal to 0. When a is equal to 0, we have u of t is equal to 0 for t less than 0 and equal to 1 for t greater than or equal to 0. The product f of t into u of t minus a is defined as f of t into u of t minus a is equal to 0 for t less than a and equal to f of t for t greater than or equal to a. Laplace transform of unit step function. By definition, we have L of u of t minus a is equal to integral from 0 to infinity e raised to minus st into u of t minus a dt, which is equal to integral from 0 to a e raised to minus st into 0 dt plus integral from a to infinity e raised to minus st into 1 dt. That is equal to 0 plus integral from e raised to minus st divided by minus s between the limits 0 and infinity, which is equal to 1 by s into e raised to minus as. In particular, L of u of t is equal to 1 by s. For a less than b, a difference of unit step functions may be defined as u of t minus a minus u of t minus b is equal to 0 for 0 less than or equal to t less than a, equal to 1 for a less than or equal to t less than b, and equal to 0 for b less than or equal to t less than infinity. Second shifting theorem. If L of f of t equal to phi of s, then L of f of t minus a into u of t minus a is equal to e raised to minus as into phi of s. By definition, we have L of f of t minus a into u of t minus a is equal to integral from 0 to infinity e raised to minus st f of t minus a u of t minus a dt, which is equal to integral from 0 to a e raised to minus st f of t minus a into 0 dt plus integral from a to infinity e raised to minus st f of t minus a into 1 dt, which is equal to 0 plus integral from a to infinity e raised to minus st into f of t minus a into 1 dt, that is equal to integral from 0 to infinity e raised to minus s into p plus a f of p dp, where t minus a is equal to p, that is equal to e raised to minus as into integral from 0 to infinity e raised to minus sp f of p dp, which is equal to e raised to minus as into phi of s. Remark. From above, we have L inverse of e raised to minus as into phi of s is equal to f of t minus a into u of t minus a, and if a is equal to 0, we have L of f of t into u of t is equal to phi of s, which is equal to L of f of t. Example 4. Find the Laplace transform of e raised to minus 3t into u of t minus 2. Solution. Express e raised to minus 3t as a function of t minus 2, we have e raised to minus 3t is equal to e raised to minus 3 into t minus 2 plus 2, which is equal to e raised to minus 6 into e raised to minus 3 into t minus 2. Therefore, e raised to minus 3t into u of t minus 2 is equal to e raised to minus 6 into e raised to minus 3 into t minus 2 into u of t minus 2. Comparing e raised to minus 3 into t minus 2 into u of t minus 2 with L of f of t minus a into u of t minus a, we get a is equal to 2 and f of t is equal to e raised to minus 3t. Therefore, phi of s is equal to L of f of t, which is equal to 1 by s plus 3. Therefore, L of e raised to minus 3t into u of t minus 2 is equal to e raised to minus 6 into L of e raised to minus 3 into t minus 2 into u of t minus 2, which is equal to e raised to minus 6 into e raised to minus 2s into phi of s, which is equal to e raised to minus 2 into s plus 3 all divided by s plus 3. Example 5. Find the inverse Laplace transform of e raised to minus 2s divided by s minus 3. Solution. By second shifting theorem, we have L inverse of e raised to minus as into phi of s is equal to f of t minus a into u of t minus a. Let phi of s is equal to 1 by s minus 3, then f of t equal to e raised to 3t. Therefore, L inverse of e raised to minus 2s divided by s minus 3 is equal to L inverse of e raised to minus 2s into phi of s, which is equal to f of t minus 2 into u of t minus 2. That is equal to e raised to 3 into t minus 2 into u of t minus 2. Unit impulse function. Impulse is considered as a force of very large magnitude applied for just an instant, and the function representing the impulse is called Dirac delta function. Mathematically, it is considered as the limiting form of the function delta epsilon of t minus a, which is equal to 1 by epsilon for a less than or equal to t less than or equal to a plus epsilon, and equal to 0 otherwise, as epsilon tends to 0. As epsilon tends to 0, the function delta epsilon of t minus a tends to be infinite at t equal to a and 0 elsewhere, with the characteristic property that its integral across t equal to a is unity. Now, the integral limit as epsilon tends to 0, integral from 0 to infinity, delta epsilon of t minus a dt is equal to 1, represents unit impulse at t is equal to a. Hence, the limiting form of delta epsilon of t minus a as epsilon tends to 0 is expressed as unit impulse function denoted by delta of t minus a. Thus, the unit impulse function is defined as follows. Delta of t minus a is equal to infinity for t equal to a and equal to 0 for t not equal to a, such that integral from 0 to infinity delta of t minus a dt is equal to 1. Laplace transform of unit impulse function. We can write delta epsilon of t minus a is equal to 1 by epsilon into u of t minus a minus u of t minus a minus epsilon. Now, L of delta epsilon of t minus a is equal to 1 by epsilon into L of u of t minus a minus u of t minus a minus epsilon, which is equal to 1 by epsilon into e raised to minus as divided by s minus e raised to minus of a plus epsilon s divided by s. That is equal to e raised to minus as divided by epsilon s into 1 minus e raised to minus epsilon s. Hence, L of delta of t minus a is equal to L of limit as epsilon tends to 0 delta epsilon of t minus a, that is equal to e raised to minus as into limit as epsilon tends to 0 1 minus e raised to minus epsilon s divided by epsilon s, which is equal to e raised to minus as. In particular, if a is equal to 0, L of delta of t is equal to 1, and so L inverse of 1 is equal to delta of t. Filtering property of unit impulse function. If f of t is continuous and integrable in the right open interval 0, infinity, then integral from 0 to infinity f of t into delta of t minus a dt is equal to f of a. Relation between u of t minus a and delta of t minus a. We have L of u dash of t minus a is equal to s into L of u of t minus a minus u of minus a. That is equal to s into e raised to minus as divided by s minus 0 is equal to e raised to minus as, which is equal to L of delta of t minus a. Example 6. A beam has its ends clamped at x is equal to 0 and x is equal to L. A concentrated load W acts vertically downwards at the point x is equal to L by 2. Find the resulting deflection. Solution. The differential equation for the given beam problem can be taken as d raised to 4y by dx raised to 4 is equal to w by ei into delta x minus L by 2, where y is equal to y of x represents the deflection with the boundary conditions y of 0 is equal to y dash of 0 is equal to 0, y of L is equal to y dash of L is equal to 0. Taking Laplace transform on both sides, we get s raised to 4 into y bar minus s cube into y of 0 minus s square into y dash of 0 minus s into y double dash of 0 minus y triple dash of 0 is equal to w by ei into e raised to minus ls by 2. Using the given conditions and taking y double dash of 0 is equal to c1 and y triple dash of 0 is equal to c2, we obtain s raised to 4 into y bar minus c1 into s minus c2 is equal to w divided by ei into e raised to minus ls by 2, which implies y bar is equal to c1 by s cube plus c2 by s raised to 4 plus w by ei into e raised to minus ls by 2 divided by s raised to 4. Taking inverse Laplace transform on both sides, we obtain y is equal to c1 x square by 2 plus c2 x cube by 6 plus w by ei into x minus L by 2 the whole cube divided by 6 into u of x minus L by 2. That is y is equal to c1 x square by 2 plus c2 x cube by 6 for 0 less than x less than L by 2, and c1 x square by 2 plus c2 x cube by 6 plus w by ei into x minus L by 2 the whole cube divided by 6 for L by 2 less than x less than L. Using the given boundary conditions, we obtain 0 is equal to c1 L square by 2 plus c2 L cube by 6 plus w by ei into L cube by 48, and 0 is equal to c1 into L plus c2 into L square by 2 plus w by ei into L square by 8. Solving these equations, we obtain c1 is equal to wl divided by 8 into ei and c2 is equal to minus wl divided by 2 into ei. Hence, the resulting deflection is y of x is equal to wl x square divided by 4 ei into 1 by 4 minus x by 3 for 0 less than x less than L by 2, and wl x square by 4 ei into 1 by 4 minus x by 3 plus w by ei into x minus L by 2 the whole cube divided by 6 for L by 2 less than x less than L. Laplace transform of periodic functions. If f of t is a periodic function with period k, then phi of s is equal to L of f of t, which is equal to 1 by 1 minus e raised to minus sk into integral from 0 to k e raised to minus st f of t dt. By definition, we have phi of s is equal to L of f of t is equal to integral from 0 to infinity e raised to minus st f of t dt, which is equal to integral from 0 to k e raised to minus st f of t dt plus integral from k to infinity e raised to minus st f of t dt. Put t is equal to u, t is equal to u plus k, t is equal to u plus 2k, etc. in these successive integrals, we get phi of s is equal to integral from 0 to k e raised to minus su f of u du plus integral from 0 to k e raised to minus s into u plus k into f of u plus k du plus integral from 0 to k e raised to minus s into u plus 2k into f of u plus 2k du plus etc. Since f of t is periodic, we have f of u is equal to f of u plus k is equal to f of u plus 2k is equal to etc. Therefore, we get phi of s is equal to integral from 0 to k e raised to minus su f of u du plus e raised to minus sk into integral from 0 to k e raised to minus su into f of u du plus e raised to minus 2sk into integral from 0 to k e raised to minus su f of u du plus etc., which is equal to 1 plus e raised to minus sk plus e raised to minus 2sk plus etc. into integral from 0 to k e raised to minus su f of u du. That is equal to 1 by 1 minus e raised to minus sk into integral from 0 to k e raised to minus st f of t dt. Example 7. Find the Laplace transform of the following rectangular wave function given by f of t is equal to 1 for 0 less than t less than c and equal to minus 1 for c less than t less than 2c, and f of t plus 2c is equal to f of t. Solution. The given function is periodic with period k is equal to 2c. Therefore, phi of s is equal to 1 by 1 minus e raised to minus 2cs into integral from 0 to 2c e raised to minus st f of t dt. That is equal to 1 divided by 1 minus e raised to minus 2cs into integral from 0 to c e raised to minus st into 1 dt plus integral from c to 2c e raised to minus st into minus 1 dt. That is equal to 1 divided by 1 minus e raised to minus 2cs into 1 minus e raised to minus cs divided by s minus e raised to minus cs minus e raised to minus 2cs divided by s. That is equal to 1 minus 2 e raised to minus cs plus e raised to minus 2cs all divided by s into 1 minus e raised to minus 2cs. That is equal to 1 minus e raised to minus cs the whole square divided by s into 1 plus e raised to minus cs into 1 minus e raised to minus cs. That is equal to 1 by s into 1 minus e raised to minus cs divided by 1 plus e raised to minus cs. That is equal to 1 by s into tan h as divided by 2. Let me wind up the session. In this session, we have discussed the method of finding solution of linear ordinary differential equations by using the Laplace transform method. Also, we have discussed Laplace transforms of unit step function, unit impulse function, and periodic function. Now you have some questions, try to work out. First one, solve using Laplace transform. 1. Y double dash minus 4y dash plus 3y is equal to 0, where y of 0 is equal to 1 and y dash of 0 is equal to 4. 2. D square y by dt square minus 9y is equal to sin t, where y of 0 is equal to 0 and y of pi is equal to 0. Second one, solve the simultaneous equations dx by dt is equal to 2x minus 3y, dy by dt is equal to y minus 2x, where x of 0 is equal to 8 and y of 0 is equal to 3. Third one, state and prove second shifting theorem. Fourth one, find the Laplace transform of the function f of t is equal to t minus 1 whole square into u of t minus 1. Fifth one, find the inverse Laplace transform of s into e raised to minus as divided by s square minus w square, where a is greater than 0. Sixth one, find the Laplace transform of the triangular wave function of period 2c given by f of t is equal to t for 0 less than t less than c and 2c minus t for 0 less than t less than 2c. Let me suggest a few books for your further study. First one, The Laplace Transform, Shom Outline Series, Shom Publishing Company, New York. Second one, Advanced Engineering Mathematics by E. Kreisig, John Wiley and Sons, New York, 1999. Hope that you have enjoyed this session. We will meet again with another topic. Thank you.